Good morning, good afternoon, ladies and gentlemen. Welcome to this series of online lessons. If you haven't already, please subscribe to the channel and leave a like for this lesson. Now, in today's lesson, we continue with the ARMA 1-1 process that asks us to derive the autocorrelation function. And basically, in the previous lesson, we talked about, or we derived this part here. Okay. Let me just do this. So we derived that part, and now in part 2 we're going to derive this part right here. So we've been asked to derive the rho k, to show that the autocorrelation function for a stationary zero mean of an ARMA 1-1 process is given by this right here. So this is the autocorrelation function at k is equals to 1. So this is the process that we've been given. All right. So now what do we need for us to derive this expression right here? So the first thing that we need is we need to know what rho k is, which is the autocorrelation function. Okay. The autocorrelation function is basically equal to the covariance of x t and x t plus k. So the covariance of xt and xt plus k all over the variance or the covariance of xt xt. Okay, when k is 0, so we get the variance. So this is basically equal to covariance. Let me write covariance before I put the certain part. So we say this is the covariance of xt and xt plus k all over the variance of xt. The variance xt. Okay. In short, this can be written as so in short, this you find this books k all over 0. So the variance is when k is 0 and the covariance of k there. So now what we are looking for in this question is when k is 1. So we are basically looking for rho 1, which will be equal to, here there will be 1. So that is for variance of xt plus 1. So the variance is constant. So that is the variance of xt, because we don't have any put k here. So which is basically equal to y of 1 over y of 0. So this is what we are looking for. If we can find y of 1 divided by y of 0, it will give us this right here. Okay. So now, how are we going to find y of 1 and y of 0? Okay. We also know that the covariance, okay, is given by the variance squared, or let me say the variance. This is the standard deviation squared, which is just the variance from 0 to infinity of the sum of some arbitrary constants plus modulus of a. So the a there should be positive. So for y1, we just need to plug in sum of y k is 1. This will be equals to the variance from 0 to infinity of phi n plus 1. And for y0, this will be equals to when k is 0. So this variance coming from 0 to infinity. Let me just excuse myself here. Summing from 0 to infinity of phi n, then phi n. So because k will be 0 here, so it will just be phi n. So that is just what we have to find. Just have to find this and this, and we plug it in on top here and at the bottom there, and we are done. Okay? But the question is, how do we get these constants here? Okay? So how we get these constants, we have to use the given definition. So the given definition is xt equals to a xt minus 1 plus et plus beta et minus 1. So these terms, okay, which are the constants, they're actually the finite or the infinite expression of these constants here. Okay, so we need to find the infinite expression of these constants here, and when we find the general term of that, that will be what we need here. Okay, and what we'll put here. So that is what we should do. So we find the infinite expression of these constants a and beta here. So how are we going to do that? We have to convert this into an infinite sum, and we'll simply transpose this part so that we get xt, then minus a xt minus 1. This is equal to et plus beta et minus 1. Okay, so now here we can factor out xt by using the backshift operator. So let me just write it down here. Using the backshift operator, I'll use, what should I use? Okay, I'll just use capital B. Okay, hope it won't confuse me with the beta here. So, okay, using the backshift operator B, so we can factor out xt here, so that xt, then we have 1 minus a, then here we're going to have the backshift operator B, okay, with 1 lag, so xt with 1 lag, that is what we have here. Then this is equal to e t plus beta et minus 1. Okay, so right here we can divide throughout by 1 over a backshift, so xt will be equal to et plus beta et minus 1. Then we have 1 over 1 minus a times the backshift. That then, if a and b are less than 1, then what we have here is a geometric expression, right? So that is if modulus of z is less than 1, then the sum of a geometric series converges to this. So the sum from n equals to 0 to infinity of z to the power n converges to 1 over 1 minus z. Okay, so in this case, z is represented by that. So you see that is there as long as there is a 1 here and there is a minus there. Z is that, and we can put it here. Okay, so basically, we are going to write xt as et plus beta et minus 1 times. So this now will become this, because this is equal to this part. Okay, so now what we're going to have is the sum from 0 to infinity, open brackets, the power n. So now this part is the z, so we're going to have it here, a backshift, then like that. Okay, then we can distribute that. So we can distribute xt is equal to, so this times that. So that will be, and I left out something here. All right, no. Okay, so that will be ET multiplied by the sum from 0 to infinity of a to the power n, b to the power n. So we can simply do that. Then plus this times that. So that will be beta et minus 1. Then the sum from 0 infinity of a to the power n, b to the power n. Okay, so these can be expanded individually. We can start with this part and that. So we say xt will be equals to, we expand this. So this will be et. Then we expand the inside when n is 0. So this will be a to the power 0, b to the power 0, which is 1. When n is 1, that will be plus a to the power 1, b to the power 1. When n is 2, that will be plus a to the power 2, b to the power 2. When n is 3, a to the power 3, b to the power 3, and so on and so forth. Same applies on the other part here. So we are going to have round. So we're going to have plus beta e b minus 1. Then we expand this. So that will be 1 plus a b plus a2 b2 plus a3b3 plus so on and so forth. Goes like that. So remember, b is the backshift operator, and I am assuming that you know how to use the backshift operator. So xt will be equal to, we can distribute. So this times that will be et. This times that will be plus a. So et times the backshift operator plus a to the power 2 et 2 backshifts plus a to the power 3 et 3 backshifts plus so on and so forth. Then plus the other part. So the part same applies. So that will be beta et minus 1. So that times that will be plus alpha beta et backshift plus a2 beta et minus 1. Sorry, this is minus 1, et minus 1, et minus 1 times a backshift plus a3 beta et minus 1 times the backshift to the power 3, the backshift to the power 2. Okay, so we're distributing this. So this times that will give us this. This times that will give us alpha beta et minus 1 times 1 backshift b. Then this times that. So again, will give us this times that will be a squared beta et minus 1 times 2 backshifts plus a to the power 3 beta et minus 1 times 3 backshifts plus so on and so forth. So now what we have here is we need to understand how to use the backshift operator. So the backshift operator is just summing, or let me say going, let's say if we have et, we have a backshift operator. This is equals to et minus 1. So there is one backshift here, which is representing one lag. So a backshift represents the number of lags that we're going to have. If we already have one lag here, and we have a backshift operator to the power 1, meaning that we're going to have 2 lags. So this will be equal to et minus 2. Okay. If we have one lag and we have 3 backshifts, so this will be equals to 1 lag plus 3 lags. So that will be 4 lags. So this will be et minus 4. Okay, I hope you get the idea. If you have 2 lags, let's say 2 lags, and you have, let's say 5 backshifts. Okay, so this will be the 2 lags plus 5 lags. So this would be et minus 7. Okay, so that is the general idea on using the backshift operator. Okay, so we can expand that. So that is xt will be equal to et plus a. So this is 1 lag. So that would be et minus 1 plus a squared. There are 2 lags here, so that will be et minus 2 plus a3 et minus 3 plus so on and so forth. Plus here we have just beta. Let me just beta. So we have beta and 1 lag. Plus here we have a beta. So we already have 1 lag here plus another lag. So this would be et minus 2 plus a to the power 2b. Then here we have 1 lag plus another lag. That would be et minus 3 plus here we have a to the power 3 beta e t. So we have 1 lag plus another lag. That will be t minus 4 plus so on and so forth. Okay, so here we can now group terms. Okay, so xt now equal to, so this has no term similar to it, so that is just et plus we have this and this can be grouped, and we can factor out et minus 1. So what we're going to have is a plus beta et minus 1. Same applies to this part, and this part can be grouped, and we can factor out et minus 2. That we're going to have plus a squared plus beta, a beta et minus 2, okay, plus here, so this one and this one can be done as y's. So this will give us open brackets. This one and that one? No. This one and this one, they have the same lag here. So this one has 4 lags. This one and this one. So we're going to have a to the power 3 plus a to the power 2 beta et minus 3. Okay, so we're going to have that plus dot. Okay, so we're going to have that right there. Okay, hope you can see that. Okay, so now this goes on and on. We can create the general term of xt. We can create the general term of xt. So first of all, these constant, we can first find the general term of the constants. Okay, that is what we are actually interested in, which is we are looking for phi n. Okay, and notice here is that at n equals to 0, phi 0 is equal to 1 here. Okay, so here the constant is 1, and now we have these constants here. So that will be very important because of where we're going. So we're looking for phi n, okay, which is the general term that we're looking for. So phi n, which is the progression of the constants, will be equal to, so first of all, the powers are increasing. We have n equals to 0, 1. We just have a. The powers are increasing. A, there is 1 here, 2, 3, and so on and so forth. So there is a to the power n. Okay, then there is plus a to the power. We see that here there is no a, but here there is a, then here there is a squared. So the following term is n minus 1, then the b is constant here. Okay, so now this will be equal to, we can factor out the a to the power n minus 1. So this is a to the power n minus 1. Then what we're going to remain with here, so the idea is that when we multiply this and this, it will give us the original term. So what we're going to remain with is just a plus the beta here. So that when we multiply this and this, we're going to have a to the power n minus 1 plus 1. So it will just remain with a to the power n, then times this will come back to that. So this is the general term of phi that we looking for. Okay, so this is the general term of phi that we're looking for, and basically we had rho k being equal to y of k over what is phi of 0 or y of 0, and y of k is equal to the variance squared, then summing from 0 to infinity of the variance n times of, the constant n times the constant n plus k. Okay, so that is what we have. So we've finally found these constants. So the general term for the constant is here. Now we can now find rho 1, which will basically be equal to y1 over y0. Okay, y1 over y0. So we can find y1. So y1 will be equals to the variance, then we're summing from 0 to infinity of phi n, then phi n plus 1. So the k here is 1, so phi n plus 1. So lucky for us, we have phi n from here. So we know what phi n is equal to. So phi n is equals to a to the power n minus 1 a plus b beta. So okay, so for n, we can simply put that, and for n plus 1, so we just find phi of n plus 1. So where there is n, we're putting n plus 1, so there will be a to the power. When we put n plus 1 here, what we're going to remain with is just 1 n. Then we have a plus b. Okay, so now we can compute y1. Okay, so when we put n plus 1 here, the same thing as a to the power n plus 1. Then you have a minus 1 outside. So this and this cancel, which will give you n. That is what I meant there. All right, so from here, we have y1. We can simplify y1. y1 will be equals to the variance squared. And you should put in mind that we've already established that y0 is equal to 1 from our previous statement here. So we've established that y0 is equal to 1. Okay, here equal to 1. That is what you should put in mind. So this will be equals to the sum from 0 to infinity. Then here we can put this. So that is a to the power n minus 1 a plus beta times, here we can put this a to the power n a plus beta. Okay, and simplify this as summation from 0 to infinity. So this will add up and give us a to the power 2n minus 1. Then this will give us a plus beta to the power 2. Okay, so now here we can simplify further. So right here we can have two sums. We can simply say this is equal to the variance, open brackets, that is summing from n equals to 0, n equals to 0, 0, okay, over a to the power 2 n minus 1, a plus b to the power 2, plus sum from n equals to 1 to infinity of a plus b to the power 2. Okay, so we can do that here. Then what we're going to have is, or just hold on, What we can do here is, I've just remembered we have phi of 0 being equal to 1. So what we can do here is that first we can go back to the general part, so that we have, from the general part, we have sum from 0 to infinity of phi n. So we want this sum to start at 1 instead of 0. So because of phi 0 being equal to 1, we cannot go directly. So let me just recap that. So we have phi of n, then phi of n plus 1. So that is what we have. So if we wanted to start at 1, so that would be from n equals to 0, 0 plus of phi n, then phi n plus 1, plus, then here we would start from n equals to 1 to infinity, then phi n, then phi n plus 1. So we'll come back to that. So, but here, what we've done is basically using the sum property. So that is a summation of, let's say, from n equals to a to b. This is basically equal to the sum from n equals to a, then we can say b, or let's say c. We can put a number here. So we can say c. We can end at c. Then we say plus the sum from c plus 1 to b. Okay, so we can do this for sums. So the reason why I didn't want to go directly, because we know what phi 0 is, and we would misrepresent the equation. So here, for n equals to 0, when you plug in 0 here, what you remain with is phi of 0 and phi of 1. Then we have plus the sum from n equals to 1 to infinity of phi of n, then phi of n plus 1. So for this one, it remains unchanged, which is we'll use the same part here. Okay, so then there is a standard deviation outside here and outside here. Okay, so which is what we have here, so which is going to be this. Okay, so now what we're going to do here, I hope I haven't lost you here. So instead of starting at 0, we want to start 1. Okay, and for the first part, we know what phi of when n is 0 is. Okay, so we don't want to disturb that. So what we've done is we've split this into two parts. That is from n equals to 0 to 0, plus from n equals to 1 to infinity. Okay, and basically we replace n equals to 0 here. We're going to have phi of 0 plus 1, then the standard deviation is outside here. Okay. Okay, then now this part still remains this part. Okay, we've factored out, in fact, we've factored out the variance. So this part will only start at 1, but it will be this part. So what we're going to have is, we know what phi 0 is. So phi 0 is equals to 1. And for phi n equals to a to the power n minus 1 of a plus b, phi 1 will be equal to, this will be 1 minus 1, so it will just leave us with a plus b, a plus b. So what we're going to have is y1 being equal to the standard deviation outside. Is it the variance? Is the variance outside? So the variance outside here, we're going to have a plus b plus, so this will remain the same, which is when we multiply phi n and phi n plus 1, we're going to have this that we had here, which is basically a to the power n minus 1. So this would be sum, but the sum will start from 1 infinity of a to the power 2n minus 1 of a plus b to the power 2. Okay, hope you're still with me. I hope I haven't lost you. So that's basically it. Okay, let me just go through one time. Okay, we were at this stage where we said phi of 1 is equal to this, and basically, which is equal to this. But we want our sum to start at 1. So we said we can split this into two parts. That is from 0 to 0. Then we say 0 plus 1 to infinity. Okay? Then from there, there's a square here. From there, we can find this separately. So this separately is when n is 0, we plug there, that will be n0 and n1. And since we're ending at 0, the sum ends here. Then plus this part, which is the variance has been factored out. So here the variance has been factored out on both. Okay. Then here from 1 to infinity of phi n. Then here, when we multiply this, we multiplied these two. It gave us this right here. Multiplying this to give us this, which simplified to this. So we can just bring this and put it here, and we will not change anything, which is what we've done right here. So we've just gotten this, which is still this. We put it here. Okay. Then we have our this, which is this right here, and we've factored out the variance. Okay. Then we can further simplify. So this can further be brought outside. So this will be right. So we want this outside here because it's a constant. So we have y of 1 being equal to variance outside. And inside here we have a plus b. As we can factor out this. So that is a plus, sorry, it's beta. Is it a plus b or a plus beta? It's a plus b. Let me just check here. So that is a plus beta. Okay, so this is beta. Okay, so beta, a plus beta. A plus beta. So it's a plus beta from here. We're using beta. So a plus beta. Then we can factor out a plus beta, that to the power 2, then summation from n equals to 1 to infinity of a plus beta. Oh, sorry, of a to the power. We can put a 2n here. We can introduce a 2n minus 1. Then we can say minus 1 plus 1. Okay, so we have introduced these two parts here, minus 1 plus 1, so they can add up, give us a 0, and we're changing the statement. So the idea is we want to make this more even, the numerator here. So this can be written as Okay, then we have a plus beta plus a plus beta to the power 2 from n equals to 1 infinity. Then this will be written as a to the power 2n. Then this will be minus 2, then plus 1, which can be written as times a to the power 1. Okay, so we want that so that we can factor out, and it can give us a nice geometric series. So this can also be factored out. So we're going to have equal to a plus beta plus a plus beta squared. Then the a comes out. Sum from n equals to 1 to infinity. Then we have a to the power 2, then n minus 1. Okay, then here we can use a bit of change of variables. So we can change the limits here. So if we transpose this side, that will be n minus 1 equals to 0. So this will be y of 1 being equal to, so that will be a plus beta plus a plus beta squared a, then the sum from n1 equals to 0 to infinity of a to the power 2. We can change this n minus 1 to the m, so that here we're going to just have one letter m. So this would be m power m equals to 0 to that. So this right here is a geometric series again. So that is a geometric series. So we can further simplify this as a plus b beta plus a plus beta to the power 2. We have a sum from m equals to 1, m equals to 0 to infinity of a to the power 2, then to the a to the power 2, then to the power m. Okay, so now this is a geometric series. Remember what we were doing. So 1 over 1 minus z equals to the sum from 0 to infinity of z to the power m. So we have n here, n, which is this. So finally, for y1 will be equal to this squared a plus beta plus a plus c squared a, then times 1 over 1 minus, so now this is our z, so this is a squared. Okay, so this is where y1 ends. Okay, so I can just do a recap in the few minutes that I have for y1. I'm doing a lot of recaps. So y1 said, first of all, we established that yk is found using k is equals to this. Then y1, simply putting 1 on k, so this will be this. Okay, so we know that phi 0 is equals to 1. So that is something that I also forgot was solving. So, but luckily I remembered on time. So, but phi of n is equals to n minus 1 plus b. Then phi of n plus 1, which is what we need here, is equals to a to the power n plus ab. So for phi of 1 or y1, because the standard deviation of, we multiply these two, so this is this and multiply by this, which is this and this being multiplied, so these two multiplied, which will give us this when simplified. Okay, then we said let me box this right here. So let me box right here. So we said we can write this starting from 1. How we can split that is we can sum from 0 to 0, then from 1 to infinity. So this is just some basic property of the summation sign that we use here. So for n equals to 0, we're going to have phi 0 here, then phi 1, then plus this, which start at 1 to infinity, which is what we simplified here. And we factored out the variance here and here. So we put it outside here. Then we put it outside here. Then we had this. So phi of 0 we know is 1 from the previous step, and phi of 1 we can find phi of 1 using the formula of phi of n. So we found that. We have this. So this we already know, we already simplified, which is this part here. And phi of 1 will simplify this. Then we start simplifying. Then here we have we want to have n minus 1 here, so that we can transpose this so that it starts from 0 and we can relate it to the geometric series. So the goal here was to introduce a 2 so that we have 2n minus 2, so that we can factor out the 2 and we remain with the n minus 1, which is what we did here. Then after that, we would simply approximate that to a geometric series. So by introducing negative 1 plus 1, which is what we need for a 2 here, so that we can factor out this 2 here, and we have an extra a here, we can factor it out. Then we simplify, then we remain with the geometric series. So we said here, use green. So here we say let m equals to n minus 1. So we transpose this, it comes here, it will become n minus 1. Then here this will be n minus 1, so we put m. Then m will start from 0 and will end at infinity. Then this is basically a geometric series. Okay, then this is this plus this, then the standard deviation is outside. Then we said that this is equal to that. So meaning that this can be written as the sum of the geometric series with a squared, like that. Okay, so that is y1. Now we need to find y0. So we have found the numerator. Now we need to find the denominator. So again, we have we know what phi n is equal to. That is a to the power n minus 1 of a plus b, beta, sorry. Then y0 is basically equal to the variance, then summing from n equals to 0 to infinity of phi n. Okay, so this basically will be when k is 0, so that will be 0, so we'll remain with that. So this basically is the variance. Again, here we need to start from 0, so I can do this in advance. So we can say from the sum from n equals to 0 to 0 of phi n by n, then plus the sum from n equals to 1 to infinity of phi n. Okay, I'm pretty sure this one will be shorter. So phi 0 will be equal to the variance. Then this will be phi 0 squared, okay, plus summation from n equals to 1 to infinity, just be phi n squared. So phi n squared. Okay, so phi 0 is equal to 1 by n squared will be equal to, so we're squaring this, so this would be this squared and this squared, so it would be a to the power 2n minus 2, okay, that is squared, then plus a plus b, the power beta to the power 2, everything to the power 2, so that is squaring that. I'm presuming you know how to square. Then our y0, I don't know, you can ask on that. So squaring, basically we have phi n, which is equals to a to the power n minus 1 squared. So we square both parts, but b power n, which is 2. So this will multiply with the power there, so it becomes 2n and 2n minus 1. Basically what we mean when we square. So from there, we now plug in y0. So y0 will finally be variance outside. This would be 1 squared, which is just 1 plus the sum from n equals to 1 to infinity of a 2. We can factor out the 2 among these so that we remain with n minus 1. Then we have a plus beta to the power 2. Okay. Then here we're going to have the variance squared, 1 plus, we can factor out the a plus b squared, so we have a plus b squared. Then here we can make a change of variables, so this will be the sum from n minus 1 equals to 0 to infinity of a to the power 2 to the power n minus 1. So these two, we can take it inside. Then we know that this is a geometric series, so we can let, okay, n minus 1 equals to m. Here we're going to have m, here we're going to have m, and here we're going to have m, which will just be a geometric series. And basically what we're going to have is y0 being equal to this 1 plus a plus b squared, beta squared, then all over 1 minus a squared from the definition of a geometric series. Okay, so now we have our y0, which is that, and our y1, which is equals to the variance squared, open brackets, that was a plus beta plus a, open brackets, a plus beta squared, then 1 minus a squared. I think that is what it was. Let me just check to confirm. All right, so that is what we have. So now remember that row 1 is equals to y1 over y of 0. We can put y1 on top there. So basically we can multiply this and that, so makes our division easier. So we can simply say, okay, let's put it squared. We can let's simplify in advance. So we say this is over everything here. So we find the common denominator here. So the common denominator on this part will be 1 minus a squared. So this will multiply with that, so that we're going to have a plus beta 1 minus a squared plus this part, which is a, then a plus beta squared. So this is a 1, so no need to put it there. Okay, so that is what we have here. Then on the numerator, on the denominator, we're going to have this here. So again, we can multiply this and this. So we have variance outside. So we can multiply this and this to find the common denominator. So that will be 1 minus a squared. Then this and that will give us 1 minus a squared plus a plus beta squared. Okay. Then from here, we just simplify. We see that this and this goes. So we're going to have row 1 being equal to, so the division here, I hope you can see it. We have this divided by this, which can also be written as, we have, can I expand in advance? So let me expand in advance. So let me expand. So this times this, everything here, we're going to have a minus, wait, before I expand, let me see. All right, let me just hold on before I expand. So we have a plus b, open brackets, then we have 1 minus a squared, okay, plus a plus beta squared, then all over 1 minus a squared. So this will be times, for times, so this will swap. It will be 1 minus a squared all over 1 minus a squared, then plus a plus beta squared. Okay, so we see that this and this cancels. So what we're going to have is row 1 being equal to a, but we can factor out a plus beta here on top, and basically we're going to have a plus beta, or we factor out 1 minus a squared plus a plus beta squared all over this part, which is 1 a squared plus a plus beta squared. So now we have reached a good way. So now the only part that is remained is simplifying here. So we further simplify. So remember, what we are looking at is we're trying to show that this is equal to, so this right here. So we're showing that it is equal to this right here. So if we check down here, there's an expansion, and down here we can factor out. So what we're going to do is basically we're factoring out. So we're going to factor out a plus b on the numerator, and we're going to expand the denominator so that see how it simplifies for us. All right, so let's simplify. So we have row 1, because we factor out a plus b outside, a plus beta. I keep saying a plus b, that's why in those written mistakes. A squared, then here we're going to remain with the plus. This will be factor out a plus b. Here we're going to have just a plus b, so we can distribute the a and a. That will give us a squared, and we can distribute the a, and that will give us a b. Hope I don't lose you there. So here we factor out a plus b. What we remain with is just the a plus b. So we distribute a times a, that will be a squared, and then a times b, that will be b, ab. And on the denominator here, we have 1 minus a squared, and we can expand that. That will be a squared plus 2a beta plus beta squared. Okay, so this would be row 1 being equal to a plus beta, open brackets, then this and this simplifies, and what we remain with is 1 minus a beta, and at the bottom this and this simplifies, so what we remain with is 1 plus beta squared plus 2a beta. All right, so there you go. So that is basically your solution right there. So I can run you through the entire procedure. So for this one, you can what you just need to know is getting the constants. Okay, so that is what you should just know, is how are you going to get the constants. So these are the constants that we got, and we derived the general form of the constant. Then we use the general form of the constant in the equations for the covariance. Then we find the variance and the covariance when k is 1 for the top part. So we can do the same for row 2. You can just now need to find y2. So now here it will be n plus 2 of n. Then you just simplify, you do the same thing that we've done. So, but for the variance, it will just be the same. So it's a pretty good example. I hope you had any you've had understood everything, and see you in the next lesson. So yeah, where you're not clear, please leave the comment in the comment section, and I'll be able to get back to you hopefully very soon. Thank you very much.